Welcome, everyone. I'm absolutely thrilled to have you here for today's explainer. We're going to unpack something really fascinating today. The hidden, honestly kind of magical technology that big tech companies use to handle literally billions of users without their systems just, well, completely falling apart. If you've ever been curious about the invisible architecture powering the modern internet, you are in the exact right place. We're going to build our understanding through a step-by-step tutorial today, so let's jump right in.
So think about this for a second. Why doesn't Netflix just totally crash when millions of people hit play on that massive, highly anticipated new season at the exact same time? Or how about Google? How does it manage to hand you search results in a fraction of a second no matter what random thing you type in? And how on earth does Amazon survive the absolute madness of Black Friday with millions of people frantically clicking add to cart all at once? Every single second, these companies process millions of requests across thousands of servers. To really grasp how they pull this off, we have to look at the fundamental problem they're trying to solve.
To make this super concrete, imagine you're opening a brand new, tiny restaurant. You've got one chef in the kitchen, one cashier taking orders, and just one table for guests. For a handful of people, hey, everything works perfectly fine. It's cozy, it's totally manageable. But what happens if, one day, literally 1 million hungry customers suddenly show up at your front door? It'd be utter chaos, right? The cashier's instantly overwhelmed, the chef can't possibly cook fast enough, and the whole restaurant just breaks down. This is exactly what would happen if a massive platform tried to run their operations using only one giant server. It simply cannot handle that kind of load.
So what's the fix? Instead of relying on one single super-powered machine, these tech giants use something called distributed systems. Basically, they use thousands of ordinary computers all working together in perfect harmony. Think of it like a hive mind. One giant, unstoppable brain made up of thousands of smaller, interconnected brains. When one gets tired or fails, the others just naturally pick up the slack. This is the foundational secret to building a truly uncrashable application. Okay, let's get into the details. Here is our 5-step tutorial blueprint for building this uncrashable architecture. We're going to cover distributing traffic, proximity and speed, decoupling, elasticity, and finally, managing the data.
Step 1. Distributing traffic to handle the millions. Starting right at step 1 of our blueprint, when millions of people type in a web address, we absolutely need a system to manage that massive initial wave of traffic instantly.
And that brings us to our first secret weapon, the load balancer. Let's go back to our restaurant analogy for a second. Imagine you now have 10 cashiers instead of one. Instead of all the customers rushing into a single line and yelling over each other, you have someone standing right at the entrance. That person acts like a traffic cop, looking at the lines and directing each new customer to whichever cashier is currently free. Well, that is exactly what a load balancer does for web traffic. Instead of one server taking all the heat, the traffic gets evenly divided among hundreds or even thousands of servers. If one server suddenly gets bogged down or goes offline, the load balancer just automatically reroutes new users somewhere else. This simple, brilliant division of labor is why websites stay fast even during huge traffic spikes.
Moving on to step 2, proximity and speed, or how we stop the lag.
Now, distributing the traffic is great, but if the actual data has to travel too far across the globe, the user is still going to experience lag. And in the tech world, lag is the ultimate enemy. To solve the physical limits of distance, let's look at Netflix. If you're watching Netflix in India, but every single frame of that video had to travel through underwater cables all the way from a server in America, it would be painfully slow. You'd be staring at a buffering wheel all day. So what's really interesting here is that instead of doing that, Netflix uses a CDN, a content delivery network. They store copies of their movies and shows in servers located physically close to the users. So when you press play, that movie isn't crossing an ocean, it's usually coming from a server sitting right in your own geographic backyard. That is the secret to why high-definition video starts almost instantly. Alongside CDNs, we have another incredible speed trick, caching. Let's say it's the day after a massive global sports event, and 1 million people go to Google to search who won the FIFA World Cup. Should Google's servers really expend the computing power to calculate and search for that exact same answer 1 million separate times? Absolutely not. It calculates the answer just once and then saves that result in a cache. When the next million people ask the exact same question, Google just hands them the saved answer instantly. Caching eliminates redundant work, and it's a huge reason why modern platforms feel so incredibly snappy.
All right, step 3, decoupling to isolate failures.
Let's move down our blueprint and see how these companies actually structure their code to prevent total systemic meltdowns.
The answer here is microservices. Decades ago, applications were built as one single massive program, but today, companies like Amazon and Google divide their software up into hundreds of tiny independent services. Look at Netflix, for example. They have one specific service just for handling your login. They have another completely separate one for generating your recommendations, another for processing payments, and yet another for actually streaming the video. They are all safely walled off from one another.
This brilliantly illustrates the critical risk of old architecture. With the old monolithic way, one huge program, if just one tiny part crashed, say the recommendation engine had a bug, the entire website would go down with it, the whole shebang. You wouldn't be able to log in or watch a thing. But with hundreds of tiny microservices, the system becomes highly reliable. If Netflix's recommendation service breaks, that specific box stops working, but because it's decoupled, you can still log in, search, and watch your movies flawlessly. The blast radius of the failure is completely contained.
Step 4. Elasticity, adapting to wild demand.
Checking in on our masterclass progress, we need our architecture to behave like a rubber band, stretching way out when we need it and snapping right back when we don't.
Picture this, 20 million people. Let's say it's 3 a.m. on a Tuesday. Only a few thousand night owls are awake watching Netflix. The system is super quiet. But then, fast forward to a Friday night when a highly anticipated new show drops. Suddenly, boom, 20 million people open the app at the exact same moment. How does the system handle that massive, instantaneous spike in demand without completely freezing?
They use a technology called auto-scaling. So the crucial point here is that there is no exhausted IT person running into a server room at 8 p.m. on a Friday, frantically plugging in physical machines to handle 20 million users. It's entirely automated. Cloud platforms are designed to detect when traffic is ramping up, and they'll automatically spin up and add brand new virtual servers on the fly to handle the load. And just as importantly, when everyone finally goes to sleep and traffic drops, the system automatically removes those extra servers. This elasticity ensures the site never crashes during a rush, and the company only ever pays for the exact computing power they actually use. It's a total game changer.
And finally, step 5, managing the data. We've reached the final step of our blueprint construction. Because handling billions of user requests is one thing, but securely storing and quickly retrieving the billions of data points they create, that is a whole different ballgame.
Think about it. Millions of users mean billions of pieces of data. Your secure passwords, your entire watch history, past orders, very specific search queries. Trying to stuff all of that into one single database is a recipe for a catastrophic bottleneck. So these companies use a really clever technique called sharding. Sharding is the process of splitting a massive database horizontally across many different machines. Each server stores only a small, specific slice of the overall data, but because they are intricately connected, together they behave as one giant, seamless database. This ensures that no single machine is ever overwhelmed by data requests, and if one database server fails, you don't instantly lose everyone's information.
At the end of the day, it ultimately comes down to this core ethos. Modern software isn't powered by one supercomputer. It's powered by thousands of ordinary computers working as one. That is the ultimate secret. They don't rely on a single point of failure. They spread the traffic out with load balancers, they cache information and use CDNs to keep things lightning fast globally, they break massive applications down into decoupled microservices, they automatically scale servers up and down, and they shard their massive databases.
So, the next time you seamlessly stream a movie, search for a quick answer, or buy a product with just a single click, just remember that behind the scenes, thousands of servers are orchestrating a perfect, flawless symphony in milliseconds, just for you. Thank you so much for joining me for today's explainer. I really love breaking these systems down with you guys. I'd love to hear from you now. Let me know down in the comments, which tech company's architecture should we build a blueprint for and explain next. Keep learning, and I will see you in the next one.